Next, we introduce two new concepts, that is the short circuit and the open circuit. For a resistor, again, on this two-terminal element, current flows into R from its positive terminal, so they are associated reference directions. If the resistance equals 0 or the conductance equals infinity, it's an ideal line. That is a short circuit. Then, for a short circuit, intuitively, the voltage must be equal to 0 because it's an ideal line. The current is not controlled by itself, but determined by the external circuit. If we regard the ideal conductor as a two-terminal element, what should be its characteristic in the UI airplane? The voltage must be 0, and the current can be any reasonable value. It's such a straight line in the UI plane. Remember what in the prior video corresponds to such a straight line? Right, very good. It's the same as a curve in UI plane of resistance when R equals 0. On the contrary, if R tends to be infinity or G is to be 0, this is an open circuit. For open circuit, there are no current, and the voltage is determined by the external circuit. So you can imagine what kind of characteristic curve it should be in the UI plane. Yes, the current is 0, but the voltage can be any value, so it must be drawn along the vertical axis. As we learned just now, the characteristic curve of the resistance have two limit points. Which limit point is associated with this curve? Right. It's the same that alpha is equal to 90 degrees when R tends to be infinity. So by comparing this video and the previous one, we can find that the short circuit is a limiting case when the resistance is equal to 0, while the open circuit is another limiting case where the resistance tends to be infinity. Perhaps some students think nothing for this conclusion. You may have been known it in high school, but this is just a start. We use this to help you to establish the view of the equivalent in UI plane. That is, two elements, if they have the same characteristics in the UI plane, we can say they are equivalent. You will see such a line in the future. It's also equivalent to other elements. Then let's talk about the power dissipated in the resistors. For associated reference directions as shown in the figure, we calculate the power absorbed by the resistor. The meaning of A is absorption. Absorbed power must be equal to U times I because of associated reference directions. U is equal to R times I, the power is equal to R times the square of I. Because all R we discuss in this lecture is no less than 0, so the power absorbed by the resistor is no less than 0 too. Nonetheless, if we mark the non-associated reference directions, that is, a current flowing into the element from the negative terminal, based on the discussion on the power of our previous lecture, we have two different ways. The first is U times I, but at this time, Ohm's law on the resistance is no longer U equals R times I. The reference directions of U and I for the resistor R are non-associated. So U equals minus R times I. Then the delivered power is equals to minus R times the square of I and is less than 0. What does it mean? It means that under the condition of non-associated reference directions, the delivered power is less than 0, and the resistor still absorbed power. Of course, we can consider it in reverse direction. Using the second memory method for the power, we're still talking about the power absorbed by the resistor. That is, the current is in inverse direction. We look upon it as minus I flows in this side, so the absorbed power equals U times minus I. However, we still have a U equals minus R times I due to the non-associated reference directions. Two negatives makes a positive. R times the square I is greater than 0. Through this simple discussion, on one hand, we review the previous lecture about two kinds of memory methods for the power, but more important conclusion is that regardless of how to define the direction of the voltage and the current for the resistor, it is always absorbed power. At last, we are going to answer the question I asked before. For a resistor, what are its rated values? There are four types of common resistors. The The first is a cheap resistor. It's very small, light, and reliable. The second is a carbon film resistor. It's very cheap and with a wide range of resistance, but with less precision. Resistors replace a carbon film resistor is called a metal film resistor. It's very reliable and with high precision. There's a power resistor which is suitable for high power. In the video before, I asked a question: what determines the volume of a resistor? We can get from this video. In fact, for the cheap resistor, it may have multi-values. For the power resistor, it may also have multi-values. So the resistance is not the key factor determining the volume of a resistor. This is why we focus on the discussion about the rated value of a resistor in this lecture. When you choose a resistor later, we should note 2 points. One is the value of the resistor, which needs to meet the electrical requirement. The other is very important, that is how much power does the resistor absorb. The absorbed power is very small for the cheap resistor, but for the power resistor, it is used in high power application obviously. Because of different power applications, it led to the different cooling needs, so the volume of the different resistors are different. Okay, that is the end of this lecture.